Hi, my name is Mark Tarnopolsky. I'm a professor of pediatrics and medicine at McMaster University. I've spent my life treating children and adults who have neuromuscular and neurometabolic disorders. As part of that, we've been doing a lot of studies in young athletes and also in older adults to try and improve their muscle function. What we're going to talk about today is creatine. There's an incredible amount of myths and misinformation about this, but a huge amount of really interesting, good science out there. And what I want to do today is go through some of the basic biochemistry. What is creatine? Where do we get it from? What has it been shown to do? What it's not been shown to do? And at the end, I wanted to show you some of the forms of creatine because there's so much out there, this misinformation, and I want to show you some really good examples of that so that when you, if you're interested in buying it and you go to buy this, you know what you're getting and you know what to look for. As a disclosure perspective, based on all of our research, more recently we started a company called Stay Above Nutrition, and we do sell some products for older adults and for younger people with obesity, overweight, and also just to improve function. And so when we talk about creatine, the first 30 studies that we did, this company was not founded and there was no conflict of interest. We have published one study since we founded the company where we've combined creatine with some protein. We call that Muscle 5, and we sell that through our Stay Above Nutrition site. So what we're going to talk about today is creatine. Now, creatine is found in every body. Every mammal has creatine. And where does creatine come from? So some people think that creatine is an amino acid, and it's probably due to the fact that there are two amino acids that make creatine. So one of the amino acids is called arginine, and the other one is called glycine. So arginine and glycine are amino acids, an essential and a non-essential amino acid. And what happens is these amino acids, which come either from protein breakdown or from the food that we're eating, are combined together. And this is predominantly in the kidney. And they make what's called guanidinoacetate. So we'll call that GAA. Okay, so what happens is that there is an enzyme, it's called AGAT, arginine glycine amidinotransferase. So essentially we form this GAA. GAA is in our blood, and then the GAA goes to another organ called the liver. And in the liver there is an enzyme called GAMT. And GAMT is guanidinoacetate methyltransferase. So essentially what it does is it takes a methyl group and it adds it to GAA, and we get creatine. So the creatine floats around in our blood, and it's taken up by a variety of tissues through a creatine transporter. So the creatine transporter is X-linked. So boys have an X and a Y chromosome, women have two X's, and the transporter pulls creatine into tissues. So creatine is found in a variety of tissues in our body. Quantitatively, the largest source of creatine in a human is the skeletal muscle, and that's where most of our creatine exists. But of course, many other tissues have creatine. Essentially every tissue pretty much has creatine. Brain, spinal cord, heart, they all transport creatine. Interestingly, sperm actually has a very high concentration because those little sperms need to make it up to fertilize the ovum. So they got lots of mitochondria in the tails, and they've got lots of sperm as well. So almost every tissue has this creatine transporter pulling creatine into the cell. Once inside the cell, there's a variety of different biochemical processes that creatine is involved in, and hence the interest in muscle performance, muscular dystrophy, which we're going to talk about as well, and human aging. So let's now talk about what creatine does in the cell. So if we have creatine, which will either come from endogenous synthesis within our body, or if we took supplementation, or if we were having meat, or fish, for example, which we'll discuss where it comes from and how you can load creatine. But let's say there's creatine inside the blood. What does it do in our body? Well, as it comes into the blood, it has to be taken up into the cell. So there is a creatine transporter. So like many molecules, we have transporters on our cells which pull molecules into the cell. So the creatine transporter will bring creatine into the cell. So this is the intracellular part, we call it. So within the cell, creatine has a variety of functions. The most common one that we know about is an energy metabolism. So let's start with ATP. So ATP is the energy currency of our cell. So almost every process that goes on, maintaining ionic balance across the cell membrane, calcium, which is released in response to muscle contraction, has to get taken back up again, and what's called the actin-myosin cross-bridge action. All of those things are required for muscles to contract. So if a brain is thinking too, we break down ATP. It's generally the energy currency of the cell. So when ATP breaks down by any one of those enzymes, we get ADP. And when that happens, the cell says, wow, we're under threat. There is a threat to our cellular homeostasis. There's a threat to energy charge. And we've got to try and maintain these ATP levels. We have a variety of different processes which help us to maintain the levels. So if there was a fire alarm, for example, and you had to sprint out, if you're doing a 100-meter sprint, in that rest to exercise transition, this happens instantaneously, but we have to buffer that energy charge. So there's a variety of pathways. One is called the myodenylate deaminase pathway, which we won't talk about, which ultimately makes uric acid. That provides some instantaneous repletion of ATP. But the next system that is involved is the creatine phosphocreatine system. So again, creatine inside the cell gets a phosphate group stuck on it. So that's phosphocreatine. So phosphocreatine is the charged form. So if we were to take a muscle biopsy and analyze how much creatine and phosphocreatine, generally the ratio is about 60% creatine, phosphocreatine and 40% creatine inside the cell. And they exist in what's called an equilibrium reaction. So what happens is that as this process goes on and a cell is under threat, the ADP that builds up is used by phosphocreatine to add this phosphate group back on. So what we get is ATP, and we reform creatine. So this is an energy buffer. And so this is one of the reasons why athletes, even in the 90s, were thinking about using this in sporting performance, because when you sprint, you have probably 8 to maybe 12 seconds of phosphocreatine, which can help to buffer this energy charge. And what happens is that as the system turns on, we also start to break down glycogen, called glycolysis. Problem with that is that we make lactic acid, and as any of you who've run a 400-meter race know, when you get around that 300 meters, your muscles are stiffening up, and that's to some extent from lactic acid. So the longer we can hold on to this phosphocreatine energy system, the faster we're going to be, and the less we have to dip into that lactate system. So a lot of sprinters, for example, 100-meter sprinters, were taking this to increase phosphocreatine, and that's the reason, so that under anaerobic, meaning no oxygen conditions, when you first start sprinting, we could buffer that energy charge. So this reaction is catalyzed by an enzyme called CK, or creatine kinase. Some of you might have heard CK, for example, if you did CrossFit and you overdid it, and your muscles were really sore, and the doctor measured your blood, they would see that the CK would be high, and that's where it comes from. It's in such high abundance inside our cells that if there's damage to the cell membrane, it will leak out. Creatine and phosphocreatine are very high in concentration in the cell. In fact, muscle has probably 80 to 90% of all of our creatine stores, and within muscle, it's a very high abundance to be utilized to buffer energy. Now, when you, for example, start sprinting and we use our phosphocreatine to recreate more ATP to keep the cell moving, the creatine concentration goes up. And what creatine does when it goes up is it forms a signal to tell the mitochondria to start working. So let's draw mitochondria here. So this is very stylized. The mitochondria, we'll just draw that out here, are the cellular powerhouse. So these are in every cell in our body except for red blood cells. And what they do is they take the oxygen that we breathe and the food that we eat, and through a very elaborate system called the respiratory chain or electron transport chain, we can take the potential energy from our food mixed with oxygen to make ATP. Now, It's an interesting organelle, but it has two membranes. There's the outer mitochondrial membrane and the inner mitochondrial membrane. And what happens is that when this is going on in this part of the cell called the cytosol, this increase in creatine will go through the outer membrane, through a protein called VDAC, or voltage-dependent ion channel. And so what will happen then is the ATP that we get from aerobic respiration will go out through something called the adenine nucleotide translocase. And in this intermembrane space, what will happen is the ATP plus creatine will form phosphocreatine plus ADP. What will happen then is the phosphocreatine then can go back out and the ADP goes in. And interestingly, when ADP goes into the mitochondria, that's something that we call in the laboratory state 3 respiration. So high ADP coming in turns on the mitochondria. It stimulates them to respire. So energy depletion, activate the mitochondria. Mitochondria also replenish the phosphocreatine, which goes back out into the cell. And this elaborate cycle is called the creatine phosphocreatine cycle. This is what you probably learned in your grade 12 chemistry. This is more advanced work that Theo Wallimann from Switzerland worked out quite nicely. And if you actually knock out this enzyme and a special creatine kinase called mitochondrial creatine kinase, mice have very impaired energy transduction if you knock these two things out. So this is an important energy system. Now, in addition to the energy supply from creatine, creatine can have some antioxidant potential as well. And studies have shown that when you load, which we'll show you in a subsequent video how to do that, tissues like brain and muscle, we do have some antioxidant benefits. We've done some studies using stable isotopes showing that when you load with creatine, like take some extra creatine in your body and increase your concentration, we actually lower protein degradation. And the reason for that is, as I mentioned, because these are in such high concentration, if we increase the concentration, we pull water into the cell. Cell transiently swells a little bit, and that actually reduces protein degradation. Some people think it turns on synthesis, but our studies and others haven't really shown that. What we did show is that it decreases degradation. But at the end of the day, you're still in a net positive protein balance, which is probably why some of the studies with exercise, which we'll talk about later, when you do exercise training, there's a slightly greater increase in muscle mass. So that's generally what the creatine phosphocreatine system is doing in our body. Now let's see how we can increase the creatine phosphocreatine. So we talked about creatine and that some people were actually taking creatine supplements. So first of all, how can you take a supplement? Well, we mentioned before that there's the endogenous production of creatine in our cells, as we mentioned through AGAT and GAMT, but we also get creatine every day in our diet, especially if we're meat eaters. Interesting, I was talking to Theo Wallimann, and he actually estimated that around 10% of the Norwegian and Danish population are getting the amount that would creatine load them just from the natural food content. And that's because of cold water fish like herring are very high in creatine. So essentially, the way we get it from our diet are meats and fish, which makes sense, right? Because as I mentioned earlier, skeletal muscle is where most of our creatine ends up. About 90% of all of the total body creatine ends up in skeletal muscle. So of course, eating skeletal muscle from either mammals or from fish is going to give you a high amount of creatine. Creatine is not in high concentration in pretty much any other food source. This is where we get most of it. So if someone is a vegan, for example, they have very low levels of creatine. So in fact, a vegan, by not taking this exogenous creatine, which for most of us, we're getting about 1 to maybe 2 grams if you eat a lot of meat every day of creatine from these sources. You get 0 if you're a vegan vegetarian. As a consequence, muscle levels are actually lower, and that's been well documented. And what's interesting is supplementing in vegans is probably a good thing because it did, in one study, it showed that there was some improvement in complex cognitive tasks, which is interesting. So if you're a lacto-ovo vegetarian, milk, and eggs do contain some creatine, not nearly as much as meat and fish. And so if you're a pure lacto-ovo vegetarian, you're probably intermediate between a vegan and someone who's omnivorous, meaning you eat meat and a variety of other foodstuffs. Now, creatine loading, where did that come from? Most of the work came from Paul Greenhoff, who's an excellent exercise physiologist in Britain, in his group, and also a number of folks in Sweden with the late and great Eric Holtman, who's one of the top exercise physiologists in the world. And they did a lot of studies knowing the biochemistry really well to say, well, if we give people extra creatine, can we actually increase skeletal muscle creatine levels, and does that improve performance? So what they showed is by taking a form of creatine, which is most readily available, creatine monohydrate. So by feeding creatine monohydrate to young, mostly males, but we've now shown, we and others, that females can load as well, taking 20 grams, which is quite a lot, and I'll show you this in a bit, what this looks like. 20 grams a day for 4 to 5 days will increase muscle creatine, so generally from about 135 millimoles per kilogram. The maximum, more is not better. You can't keep going up and up and up. It's probably around 160 millimoles per kilogram dry muscle mass. Doesn't seem like a lot, but what those early studies showed is that in repetitive, especially repetitive, high-intensity sprinting performance, there was improvement. So you get on a bike and you do 6 seconds as fast as you can, wait, do another 6 seconds, that sort of activity. So if you think about something like soccer starting and stopping, hockey starting and stopping, weightlifting, etc., that's probably where you're going to see most of the benefit. And in fact, that's what most of the studies have shown. So you can load your muscle with creatine, either eating a lot of fish and meat, which may not be the best thing for the planet. So to creatine load your muscle optimally to this level, you can either eat a lot of herring, a kilo or so of beef, but most people don't do that. So one of the ways to take it is an exogenous form, creatine monohydrate, 20 grams a day for 4 to 5 days, and you'll get this loading. However, Eric Holtman showed in 1996 that if you take 3 grams a day for a month, you will actually get to the same levels. So that became much more practical for people, because certainly as someone who's tried it, taking 20 grams is just disgusting, and it's really hard to do, and I don't think many people could continue that. So taking 3 grams a day, you get to the same level after about a month. The other thing that they showed is if you take the loading dose, we call it, so there's 20 grams for 4 to 5 days, and drop to 2 grams a day after a month, you're at about the same level as well. So I really don't see much of a value in the 20 grams other than causing some side effects. And if you keep doing that, you're just going to end up with more in your urine and potentially increase the risk of side effects. Certainly on the 3 gram per day dose, which we've given to older adults for 3 months, 4 months, 6 months, and a variety of other people have shown that sort of a dose does seem to be very well tolerated. There are a few people that we and others have seen in our studies who can get some gastrointestinal upset, and it doesn't seem to be age or sex related or even disease related. So we've had big, huge bodybuilder types who just were intolerant of it, and it caused them a lot of gastrointestinal upset. With creatine or any other supplement, listen to your body. Start off low. Take it with food, see how it works for you before you try anything. And certainly before performance, if you're an athlete, you'd want to certainly try this to make sure that you tolerate it. Most people tolerate this very well. And as mentioned, the 3 grams a day in an adult, which works out to around 50 milligrams per kilogram, and that's for a healthy individual, seems to load quite well. We've done studies, which I'll talk about in Duchenne dystrophy, where we found that closer to 100 milligrams per kilogram per day, which would work out to around 7 grams or so in an adult, was required. And that's because in muscular dystrophy, when we have damage to the muscle membrane and you're leaking out CK, you're also leaking out creatine. And so we need to provide a little bit more to try and load muscle. And interestingly, a study in Belgium did show that boys with Duchenne and those with Becker dystrophy, a very similar disease, did actually load muscle when they took creatine. And I'll tell you a little bit about our study in just a minute in boys with Duchenne dystrophy. So that's the standard loading for healthy young people who are trying to increase muscle mass and strength, and also for older adults. So let's see what the studies show. So what have some of the studies shown? As mentioned, the creatine literature really started in the exercise physiology, sports nutrition field. And as one might expect, the studies first showed that there's an increase in high intensity performance. So again, it's not a huge amount, 1-2% in most of the studies, and these are repeated Wingate sprints, higher intensity type of activity, which I've mentioned some of the sports, hockey, for example, starting and stopping those brief sprints for 5 to 10 seconds, and that type of activity in a controlled laboratory environment. And subsequently, many of my colleagues around the world have also shown in simulated sports performance that there is this improvement. So the evidence for this is pretty much unequivocal. The next, increase in muscle mass and strength. So again, when one does weights, if for example you're doing 3 sets of 10 repetitions, you're doing a lot of anaerobic activity, and the creatine's been shown if you do weight training over a period of time, you actually gain more muscle mass and more strength. People have shown that in younger adults, they've shown it in women, we've shown it in older adults, as have many other folks. Phil Chillibeck and others have clearly demonstrated that if you take creatine during a period of weight training for 2-4 months, for example, that there is a greater increase in muscle mass and in many cases strength as well. So those are definitely things that have been shown, and this is really the most solid bit of evidence. From a performance perspective, endurance. Now this is a very controversial area. So one of the earlier studies that was done in Scandinavia showed that when runners went out and they were doing a performance trial on a hilly course, taking creatine actually was deleterious. And part of the reason for that is likely that, as I mentioned before, when you take exogenous creatine to load, for the first 7 to 10 days, you actually increase the intracellular amount of water. Now again, that turns around after time because the cell gets used to it and wants to get rid of that water. But if you're loading and then you go out and do a run, you've got an extra 1 to 2 kilos that you're carrying. And we know that carrying an extra 1 to 2 kilos, if you do a 20 or 30K run up and down hills, that's going to impede your performance. However, there have been others that have shown an improvement in some of the metrics of muscle using MR spectroscopy with creatine. So again, this is a little bit equivocal. I personally, as an athlete and working with athletes for 30 years, if you are doing runs up a hill, for example, where it's weight supported, taking creatine is probably not beneficial. A hill climb in the Tour de France, probably not beneficial. However, if you're on the flats on a bike where you're weight supported and you just need that extra power, there may be some benefit. So this is probably contextual as to whether there's a benefit, but this is really where we see the benefits here. And so one can imagine, in crossfitting, weight training, and for our interest in our patients and also older adults who become sarcopenic and have small, thinner muscles and are at higher risk for falling, this is where we really thought that there'd be a benefit. And we published 2 clinical trials showing that there is an improvement if people train with creatine versus training with a placebo. More recently, as I mentioned, and this is in disclosure because we did this study after we started the company, when we combined high quality protein with creatine, we actually saw a better improvement in older adults when they did that with fish oil as well compared to taking a collagen. Now again, that original study was done by Johnny Parisi and Stu Phillips, and we just replicated their data and put it into a formulation which is a little bit more palatable. So these are the main things that creatine does. However, there's a whole host of different medical conditions where creatine could be of some benefit, and we'll talk about those in just a minute. So I first became interested in creatine back in 1999. So back in 96, we saw the study where they showed that you can load with 3 grams a day, which seemed practical for the general population. And in 1999, my first undergraduate and PhD student, Johnny Parisi, and I analyzed muscle biopsies from patients with a variety of neuromuscular disorders. So in that group, we had patients with mitochondrial disease, we had patients that had muscular dystrophy and congenital myopathies, and we had patients with inflammatory muscle disease. And what we found is that the total in phosphocreatine content was quite low. So given that it was low, and we know, as I mentioned before, is that if there's damage to the muscle membrane, we leak out creatine kinase, which is one of the hallmarks of muscular dystrophy, and some of our mitochondrial patients as well, do they need more creatine, and would there be benefits? And what was interesting is we did this on muscle biopsies, but other people had done some studies using what's called NMR spectroscopy. So they could measure phosphocreatine using a fancy thing where you look at the resonance of the phosphorus molecule. And what they found is that there was lower concentrations of phosphocreatine in brain of patients who have mitochondrial disease, and also they found in muscle of people with inflammatory myopathies. So why don't we take the information from what we learned in the sports arena and bring it to our patients who are deficient? In my overall thought process, I think it's, and there's a lot of evidence to support this, that a deficiency state, when we replace it, you're more likely to see benefit versus someone who's already at a sufficient level, and we try to supercompensate. And we felt that our patients were an ideal source. And the two groups that we wanted to work with was muscular dystrophy and also the mitochondrial patients. So we did a study in patients with primary mitochondrial disease. Now this was a short-term study, and in those individuals what we found was an increase in high-intensity exercise performance. So we did all sorts of fancy muscle contractions, and just like what people had shown in young healthy people and older adults, there was this shift upwards when you're doing higher intensity activity. Now, it was for a very short period of time, so we didn't see an increase in what's called the VO2 max, or their oxygen consumption. But certainly when one thinks about the creatine levels being low in the brain, and things like a stroke, for example, are patients with MELAS syndrome, where they're prone to stroke-like episodes, would there be benefit? Now, really difficult study to do. No one's going to be making billions of dollars on creatine, and hence that clinical study, which would probably cost $100 million, will likely never be done. But low-hanging fruit, it certainly is something that makes a lot of intuitive sense, and the risk-benefit ratio is quite favorable. So the other thing that we did, now and I'll get back to the mitochondrial diseases, we combined it with different compounds. So in the mitochondrial disease, what we hypothesized, and Dr. Flint Beal and I hypothesized this back in 2001, and that is for mitochondrial, many neurologic disease, the cell can only die so many ways, and it's not just one way. So there's energy deficiency, there's mitochondrial dysfunction, there's what are called free radicals, and in some cases something called apoptosis, and neuronal excitotoxicity. So to optimally target these complex diseases where all those processes are going on, one compound's likely not sufficient. So we hypothesized in mitochondrial disease that we would use what's called alpha-lipoic acid, which is a mitochondrial antioxidant. We would use coenzyme Q10. We would use vitamin E and creatine. So what we're doing here is that we're providing antioxidants inside the mitochondria, we're providing antioxidant protection to the membrane, and creatine for the variety of reasons that we've talked about. And when we actually combined all of these in a clinical trial, randomized double-blind trial, self-funded, no company involved, and we weren't doing anything from our company, we found that there was lower lactic acid in our patients, meaning improved mitochondrial function, and a reduction of what are called free radicals or oxidative stress. So that group, that's about as far as anyone's gone as this combinatory strategy. This is now part of the Inherited Metabolic Disease Program in Ontario, and it was the first randomized double-blind trial in patients with mitochondrial disease, obviously with creatine as an essential component of that. The other one was muscular dystrophy. Now, this probably holds true for most of the disorders, because in our congenital myopathies, where there's weakness but no damage, i.e. no release of CK, we saw also very low levels of creatine phosphocreatine. However, muscular dystrophy, the most common type that's out there, is Duchenne muscular dystrophy. It's an X-linked disorder. It affects about 1 in 3,500 live male births. And because it's so common, we could do a clinical trial. So I teamed up with my colleague, Dr. Doug Bigger from Toronto, and we had 30 patients with Duchenne dystrophy. They were all ambulatory, so they could walk, and we randomized them to creatine monohydrate, again looking at about the 100 milligram per kilogram per day dose, and they were on creatine, a washout period in placebo, or vice versa, and it was a double-blind study. And in that study, what we showed was an increase in muscle strength in the dominant hand. We showed an attenuation of the loss of strength because they're progressively getting weaker. And we also showed an increase in muscle mass when we did what's called a DEXA scan. So based on that study, and then studies came out by my colleague Maggie Walter in Germany, studies came out in Belgium as well, and also in the United States. Those all were showing similar findings. So something called a Cochrane review was done, where all of the world literature is analyzed for its validity, the risk of bias, et cetera, and all of them were put together to say, does this actually work? And the conclusion was that there's about an 8.5% increase in strength in patients with muscular dystrophy who take creatine. We and others have clearly shown an increase in lean body mass or muscle mass. And in the Cochrane review, in the 4 studies that at the time in 2013 when it was published, had looked at how people felt, that people actually felt better when they were on the creatine. Now, there's a few disorders that have a little bit of a caveat. We did a study in myotonic muscular dystrophy of over 30 patients, and we didn't see a benefit in those individuals, but they were not exercising. So it is likely, and we now are doing a study where we're using creatine in myotonic dystrophy patients to look at the interaction with exercise to see if it's like our older adults, that it accentuates the benefit. So we'll see what that shows. We do know for sure that in our myotonic patients, there's a dramatic improvement in strength, function, and mitochondrial capacity when they do exercise. So we're going to see whether creatine helps that. But all comers, when we look at muscular dystrophy, the Cochrane review showed some benefit. From another metabolic myopathy perspective, in McArdle disease, where you have a phosphorylase deficiency and don't break down muscle glycogen, again, recall that when we first start exercising, we need to use phosphocreatine breakdown, and then we activate glycolysis under anaerobic conditions. So in that rest to exercise transition, we go from phosphocreatine to anaerobic glycolysis, but if it's blocked with McArdle disease, you're going to crank through your phosphocreatine. And that's what we knew in the world literature. And so a very top researcher in Germany, Matthias Vorger, did a study in creatine, again at about 100 milligrams per kilogram, showing some improvements. Keep in mind, when they went to the higher dose, equivalent to taking 20 grams a day, it actually was deleterious to patients. Probably because of an interesting twist that creatine can inhibit something called phosphofructokinase, PFK. So phosphofructokinase can be inhibited by high doses of creatine. And our patients with McArdle disease rely on flux through this pathway, so it probably at high doses became deleterious. Low doses benefit from more phosphocreatine. High doses, you inhibit the compensatory pathway. So there's a variety of disorders where creatine is a benefit.